Okay, so hello everyone. I'm Soucheiron, and today I'm gonna talk about computational complexity in Python. So, what's this talk gonna be about? If I get past the next slide. So what's computational complexity? It's a theoretical branch of computer science. It came from mathematics, pure mathematics, so Turing and all this kind of stuff. And basically it divides all algorithms in groups. These groups are have many differences, but the most famous ones and the ones that you will be working on is Pn and NP, and then the linear ones. That's basically a constant time. Besides that, there are a lot of other classes that are more complex than these two, and every time they get more expensive. And basically what you're going to have is you end up with algorithms that basically run in more time than the universe has had. So you don't want to get there. So, this talk is basically something that in programming we call the big O. We use a notation called O to explain what's the complexity of an algorithm. And then you'll see something like O(n) or O(n) squared or O of n log n, for example. This means that these problems have this kind of complexity. So, for example, a complexity of n squared is bigger than a complexity of n log n, and n log n is bigger than n. So you always want to try to get the smaller complexity possible to solve a problem. So, if you have an algorithm, how do you know what is your complexity? So basically what you need to do is, beforehand, you need to cut your algorithm in small pieces. So each part of your algorithm needs to be separated, and then you can build basic blocks with that. Once you have that, you have to take the piece that has the bigger cost. So if you have two big chunks of code in your class or your method, and you want to see which one is the cost of your whole method, you just need to take the big one. And then you have to discard constants. So for example, if you have 2n, it will be exactly the same as n. And you'll say, why is that like this? The reason is very simple, because it doesn't matter how big your constant is. Eventually, if the n is big enough, it won't matter. For example, if you have something like, let's say, 4n cubed, if the n is at the vicinity of the millions, the n cubed is going to be so huge that it doesn't really matter if you have here a 4 or a 5. I mean, the difference is small, but if instead of n cubed you have n squared, this is going to be billions of times faster. So you really are interested in the exponent here. This is what's going to matter the most. So let's go through these examples. We have n factorial, n cubed, and O1. So basically n factorial wins because it's the bigger one here. If we have 5n factorial, a 5 doesn't matter, so we get n factorial. O3 is exactly the same as O1, it doesn't matter. You'll get the answer independently of the length of your entry. Sorry about that. Okay, and then same here, n cube, and n cube is bigger, so you get this right. So let's get some examples of what's the complexity of some algorithms, so you can see. Let's start with an easy problem. This is it a permutation? So basically we want to have two strings, and we want to see if the first string is a permutation of the other one or the other way around. So we have two strings here. I am Lord Voldemort and Tom are Polo Riddle, and we want to see if these two strings are a permutation one of the other. So basically what we do is we get all the permutations from the first string, And for each permutation, then we try to see if it's equal to the second string. And then if it's the case, we have found a permutation, so this returns true, otherwise we will return false once we've gone through all the permutations of this. So what's the code of this? Can anyone guess? What's the cost of running this algorithm? Close. He said n factorial, so he's very close, but not really, because here we have a join, and this join will cost n again. So it's n per n factorial. It's a slightly bigger than n factorial, but not incredibly worse. I mean, it's not that important anymore, because n factorial is really, really bad. You don't ever want to get here, okay? So let's go to a better solution for this problem. So what's this about? What we're doing is we're taking the longest string from the two strings we have, and then for each character we have in this string, what we're gonna do is count how many appearances we have from this character in each one of the two strings. Then if the value for all the characters in the longest string is the same as the number of counts for the second string, it means the permutation of the first one. This is also very stupid and naive, but it works. So if you write unit tests on this, it will happen exactly the same as the other one. But this is slightly better. So take another guess. What's the complexity of this? That case is a factorial. I don't think so. No. N square, exactly. So the longest string has a longitude of n. So for each character you have to go through this string again, so n times n, and then the other one, but you don't care about this one because you're doing it twice. So it's n squared. This is bad. I mean, we can do way better. So next solution. This one is easy. In fact, some people will say that this is the most Pythonic way to do this, but I'm still not happy with this. We can do better. What we're doing here is we're sorting the two strings. If the sorted strings are equal, then we're done. In Python, this is n log n. So sorting each one of the two strings is n log n. We're doing it twice, it doesn't matter, n log n again. So how can we do it? This is what's going to happen. What we're doing is using a counter. What's this counter doing is basically returning all the instances of each one of the objects that's inside an iterator. And if this object that it returns is the same, then we're done. So what's happening here is this is on, and the not equal is on again. So we're basically running in on altogether, and we're getting the same result. It's interesting to know how counter works, but I don't want to go deep into it. It basically constructs a dictionary, so you can count all the occurrences of each element, and you can check the code inside the collections library if you want to. I don't want to go much deeper on this. So, does it really matter? Yes. A lot? Of course it does. So, if we start with the simplest one, O1, it's the blue line here. On is all the way down here. Then we start increasing with n squared here. No, sorry, this is n log n squared. Here we have 2 at the power of n, and here we have the n factorial. So you can see the difference. Even if we're in about the number 6, we're already somewhere around here. So just imagine what happens if your n is something like 1,000. You don't want to be there. Actually, this morning when I was writing the code for the permutation code, I wasn't able to finish the execution of the permutations for this string that I showed you. I had to use Roma as a permutation because otherwise it took forever and I got tired of running it. And this is a small string. Imagine something like 200k file. You don't want to get there. So what is this useful for? To understand this, we have to dig very deep into the language. So we'll start understanding how Python lists work. So basically a list is a C object that looks like this. What this means is that we have a pointer to the head, the point of where the object starts. Then we have, no sorry, this is the pointer to the head. And this is the size of the array. What's going to happen is that when we have an array that looks like this, so basically we have an array of pointers that point to the real objects, and then we want to add a new entry. What we do is we will grow this list, and then we will insert it. And this is very important to understand why insertions are so expensive in Python if you want to insert in the middle of the list, but appending is so cheap. Because appending is very easy, you just have to increment the pointer and add it at the end of the list. On the other hand, if you want to insert, you have to move everything one position down. So it's not a linked list. To be able to access to an arbitrary position in linear time, that's what you want to do, then you need this. So, what does this translate to? I'll go one by one for you to understand. In this case, average case and amortized worst case is exactly the same. Average case means what's the average cost of doing an operation, and amortized worst case is what's the worst case you can have. In lists, this doesn't matter. In dictionaries, we'll see that this matters a lot, but we'll get to it. So, copy. If we want to copy a list, in this case, we have to go over through all the list. So basically, it's ON. It's the size of the list. If we want to append, we just need to increment the size of the list and then add an entry directly here, so we don't need to move anything. So it's a 1. Oops. Sorry about that. If we want to get or set a position that already exists, it's the same. We can go directly and change the value. O1. Iteration is basically the same as copy. We have to go through all the lists, so it's ON. Sorting uses team sort, so it's n log n. And finding an occurrence of an object inside list is ON. This is very important because this is one of the reasons where you're going to choose one or the other data structure. So basically, if you need to do this a lot, you'll probably want a dictionary or a set. If you don't do this ever, you'll probably want a list. And the last one is important too. Getting the length of a list in Python is a 1. So if you want to get the length, you don't need to go over through all the entries on the list, but you get it directly because it's stored here in the struct. So let's go to dictionaries. This is more complex. I don't want to go through what all these fields are, but they're used to know how big the dictionary is, how big the structure that fits all the entries in the dictionary are, and what's the current size and stuff like that. So how does a dictionary work? Basically, you have an array of values that you want to store in the real real dictionary. So this is the real dictionary. So what you're gonna do is, once you get the key, in this case A, what you're gonna do is hash the A, and then you will get a direction. So this means that you go to position 0, and then that's your position. So the nice thing about this is that if the hash is fast, then you always find the place on your table you want to go in a very fast way. So going to the place in the table with your key is instantaneous, basically, unless your table is huge. What's the problem with this in Python? There's no way to make this hash not have collisions. So if you're really, really unlucky, what may happen is that when you try to hash B, it will go to the same place as A, and then it will get assigned to another place. That's what's happening here. That is trying to go to 3, but then it ends in 5, right? The problem is that in the worst possible case, what's gonna happen is that all your entries collide. So basically, you will try to insert A. That will work fine because it's the first element, there's nothing there. Then when you insert B, it will try to go to the same place as A. And then it will go somewhere else. Then you try C, it tries to go to A again. Then it will try to go to B. And then you will end up going through all the entries in the dictionary until you get to insert the value. This is awful for performance. It's very unlikely that you will end up having this, but it may happen in the worst case. So here's what happens. This is the reason why here in the worst case changes in respect to lists. The average case is usually very fast, but if you're really, really unlucky, you may find that accessing or writing some values in your dictionary is extremely and painfully slow. So, copying a dictionary needs to go through all the keys, so it's ON, and worst case is the same. Get item, the average case is 1, so in most cases we will basically get instantaneously the entry, but if we are really, really unlucky, we will get ON. And then, on average, we have to consider the worst case, and in this case, thankfully, is ON, but we don't really need to worry about this because it happens on very rare occasions. Setting has the same problem as getting. If there are a lot of collisions, we will get to ON. Deleting has exactly the same problem, and iterating is basically the same as copy, so we'll get to ON again. Yep.
Another question. Does Python use the same hash function every time, or does it tune it in a way to, it's always the same hash function?
I think it's the same hash function, but it's prepared to handle very well when instances are continuous. So if you're hashing A, B, C, D, E, it will work very well, but you may be really unlucky. It's not a cryptographically secure hash function, so it's not intended for that, but it's made in order to get a same distribution of the data, so you don't get many collisions, and it needs to be really fast.
I guess that the size of the hash might be important, so, because if you have many different objects, perhaps you need a larger hash, but
in the end you do a modulus with the size of the table you're working on, so it doesn't matter that much. But I honestly don't know what's the hash function. I only know that it's made especially to make consecutive entries not fall in the same place. Yep.
Have they announced what kind of objects, what kind of keys may collide? For example, having sets of lists of keys that would create collisions.
No, I should check the hash algorithm. I have no idea how is it made, but I think that with the way it's made, it will be possible to make a dictionary that will collide on purpose. So you can add entries that collide on purpose if you want to. I don't know why would you, but you could theoretically. Okay, so next one, set. Oh, sorry.
And ahead in space, all these things are about type.
Yeah.
In space, because maybe we have a dictionary with 3 elements, and what is the cost in space? Because the infinite dictionary will be.
I don't remember exactly. I believe the initial size for a dictionary is 8 entries, but I don't I'm not sure if it's 8 or 4. I should check it. I saw this afternoon, but I don't remember. I'm pretty sure it's 8. And from that you start growing, and you can call a function that resizes your dictionary with the data you have in this moment. But in most cases you don't really need to do that manually, unless you're adding and removing a lot of keys at the same time.
Excuse me. Collections, I think they have other containers, like the default dig.
Yeah.
Do they have the same cost or is different?
Yeah. Default dig is a special case of dig that basically returns the default value when there's nothing in it, but otherwise I believe it's exactly the same and uses the same underlying mechanism.
Is checking for a key in the dictionary that is not in the dictionary the worst case always or not?
No, because if you go here and you're checking for a key that's whatever, and it surprisingly gets to the only position in the table that's empty, then you can return in O1.
Okay.
So finding a key that's not in the dictionary, it's O1, and in the worst case is ON. So the worst thing that could happen is that you're trying to find a key, then you get a collision for your key that doesn't exist, and then you start going through a lot of collisions. That's a worst case, but again, that doesn't happen much. So sets. I guess you all know what sets are. A set is basically a list without repeated elements, and you cannot access a position inside a set because there are no positions. It's just a group and an ordered group of items. So what are useful sets for? Sets are basically dictionaries, but optimized for doing unions and intersections. So if we want to find an element inside the set, it will happen exactly the same as in a dictionary, O1, but in the worst case, you will have a lot of collisions, we'll get ON. For a union, it will take ON in both cases. Union is basically having two sets and joining them together. So for each element of the set, you have to check if it's in the other set, and if it's not on the other one, you just, I'm not explaining very well. Basically, if you have two sets, and all the elements of the first one and all the elements of the second one will be in the result of the union. The intersection means all elements that are both in S and T, being S and T two sets. So the average case is ON, but in the worst case, if we find a lot of collisions when looking for each element of the intersection, we may go to N squared. Again, this is very unlikely, but it may happen. For the difference, it's basically the same as the union, ON. And symmetric difference, or short, has the same problem that the intersection. So, what do I want you to get from all this explanation that probably sounds like gibberish? The main thing is that you need to use the best the structure for your use case. When you have a problem, you need to understand very well the problem to make the data structure that's useful for your problem. Otherwise, you will have to go to do expensive algorithms to get the information that you could get for cheaper if you chose the right data structure before. If you absolutely need to use an expensive algorithm, and that does happen, especially those of you who do data science or work with DNA and stuff like that, the first advice I'm going to give you is try to reduce N first. So if you can do a projection, do it. It will always go faster, especially if it's an expensive algorithm. Or if you can't, try to split the problem into smaller chunks. Because when you're working with exponentials, it's always way cheaper if you can split that. I mean, do the math. It's way cheaper. The other thing that we need to think about is that sometimes slower is okay. So if we know that we're sorting strings that are something like I don't know, 5 characters, we just don't care. I mean, sorting 5 characters, you can use n to the power of 5. Who cares? I mean, you can do it in n log n, but it's okay. I mean, it's gonna take like 0.1 milliseconds. No one will ever complain about that. So, I'm sure you have seen this. Premature optimization is the root of all evil. If you have to choose between making complex code or making efficient code, unless it's really, really important and it needs to run a lot, you just don't care. Just forget about it and get it working. And the people that's gonna work with this code after you will be happier because it's easier to understand. And the last one and more important one, avoid expensive algorithms when you can. So if you can do something in ON, do it in ON. Don't try to make it O square or something like that. This may seem really, really stupid. I mean, it's obvious, but sometimes we don't realize how expensive is the stuff we're making and how slow it's because of that. And well, that's all I have for now. If you have any questions, besides how to import anti-gravity, I think it's not in the standard library, I'll be glad to answer.
Does the set have any condition to put the elements need to have the, to know when, if an item is inside a set, how do you know if in O1?
Every item you insert into a set needs to be a hashable object. So basically you need to be able to put it into a dictionary as a key. And then just imagine a set, a dictionary with the actual value. So it's basically the same. And then you can use the same mechanics.
Is all these the same for other implementations of Python? It's dependent on the...
I think all the implementations we use basically the same because I don't think you can do better. But you could get an implementation that doesn't follow these principles. I don't know why someone would do that. I think this is true for most languages. This is an explanation for Python. But I took some of the examples from a presentation that's made for Objective-C. So it's, yeah, I'm still be happy. Most languages just have the same data structures and have the same implementations or very similar implementations. But there are a lot of other data structures that have slightly different costs for different operations. And depending on your problem, that will be the way to go. Sure. Yeah.
When you have a dictionary, and you have the dictionary and you add the element, it should make all the case. Like, if you know the dictionary, the element, the case can change.
Yep. Yeah. There are cases where inserting into a dictionary will trigger a resize, and this resize can be incredibly expensive because one of the things that may happen is that all the keys are reordered. So this means that for big dictionaries, this could cause really slow operations when you're not expecting it. But yeah, this is a side effect of it. Yeah.
This will be the worst case of the dictionary inserting element.
Yeah, and it's ON. Yeah, you have to go through all the dictionaries, so it's ON. Anyone else has any other questions? Yep.
I don't know if you remove an item from a collection set or whatever, it triggers out the garbage collector to remove that from the RAM or?
Well, sets in Python are immutable, so you can actually remove anything from a set. But on a dictionary, I think that you're doing the wrong question here. So the thing is, when you're removing an element, what's going to happen actually is that you have an object somewhere that's losing a reference. So if the reference count is down to 0, then it may get removed in the next garbage collector run. But you don't have control on when this is going to happen, and this is dependent on the implementation of your Python interpreter. So this will change in CPython, in JPython, in PyPy, or whatever you're using. So I honestly can't answer these questions. I'm sorry. Okay, I think that's all. Thank you very much, guys. They tell me that it's time for a 5-minute recess, so if you wanna go around.